Hi folks, welcome back to Math with Captain Rod. I'm making this video here to try to help you understand how you do what's called a limit proof, or how do you prove the limit of a function is a certain value. So this is a topic that just gives introductory students all sorts of trouble, probably because it's the first thing that's maybe a tad on the abstract side. First of all, you have to understand, again, what a limit is. Right? A limit is a value that a function is approaching as x goes to some number. Okay. Now, this isn't really about how you find limits. It's important that you understand what a limit is. Right? It's what is a function approaching as x goes to some value. Now, there's a certain language to this here. Right? So this is epsilon here. It's the Greek letter epsilon, which typically represents small changes in y. Usually, we're talking about small positive changes in y. And then this is the Greek letter delta, which represents small changes in x, again assumed positive. So these are also called epsilon delta proofs. So let me talk about the fundamental idea here first before we look at an example. And as usual, I'm going to look at a kind of a very, very simple example to try to keep the concept clear without it getting too ridiculous or mucked up here. But so let me just talk conceptually here. Imagine we have some sort of function. And we have some value here. I'm going to call it x sub o here. And imagine that, I'm actually going to put a hole in it. The function doesn't necessarily have to have a hole, all right? But I'm going to put one there because I think it'll help the picture look a little better here. So here, we're going to imagine this. So the idea of a limit is basically this. This y value here is going to be the limit, L. The idea is to show that, and let me back up. Think of the epsilon as a challenge, okay? And imagine somebody challenges you to get arbitrarily close to this value here. And what that means is this: if I pick a small value vertically, and we're going to call that value epsilon, and we look at like here and here. If we go up here now, this is L plus epsilon, and this one down here is L minus epsilon. So what we're kind of looking at is a range, which is the limit, whatever that is, plus or minus epsilon, where epsilon is some small positive value. The idea is, for any given epsilon that's arbitrarily small, can I find a delta? All right, so we look over here now. This value is going to be x sub o minus delta. This one is x sub o plus delta. And the idea is, for any given epsilon that somebody gives me, can I find a delta such that if I stay in this range, x sub o plus delta and x sub o minus delta, then the function will stay vertically in this range. What I mean by vertically is this: the function will be less than the limit plus epsilon, and it will simultaneously be greater than the limit plus epsilon. So the idea is, for any epsilon somebody gives me, can I find a delta such that as long as we stay in this range, the function vertically stays in this range? And that means that the function is heading towards mathematically guaranteed whatever that limit is. I guess I should put this on the graph. So that's my explanation of it. I don't know if you folks can follow that or not, but let me go through an example with, again, a simple function. Now, I do my limit proofs a little different than some people. I like to do this kind of I take sides on it, basically, because I think that helps people understand this. Maybe I'm wrong about that, but what we're going to do here is we're going to try to prove that the limit as x approaches 2 for this function, 2x plus 1, is equal to 5. Now, you might look at this and say, well, it's obviously equal to 5. Put in the 2. 2 times 2 plus 1 is 5, just like Captain Rod said. Put in the number. If you get a number, you're done. Okay, that's not the question, though. The question isn't to calculate the limit. The question is to prove that the limit is this value, and those are different things. So we're going to take a look at this graphically here. Here's x equals 2. And then on the graph here, here is our limit, which is L, which is, we believe, equal to 5. And what I do is I kind of look at this piecewise here. All right, so now somebody's going to give me what I call a challenge here, an epsilon. And then the question is, can we find the appropriate delta that goes with this, that guarantees, as long as we stay in the region 2 minus delta, 2 plus delta, that the function will stay within 5 plus epsilon and 5 minus epsilon. And so what I like to do is look at this kind of two ways here. Or I'm sorry, two sides. So this x value is going to be 2 minus delta. The corresponding y value here is 5 minus epsilon for any epsilon. And then we're going to go to the other side. This is now 2 plus delta. The corresponding y value is 5 plus epsilon. Okay, now here comes the proof so far. We need our function, which is 2x plus 1. Right now, imagine we're here somewhere. We want the function to be above this, meaning greater than 5 minus epsilon. And you'll notice that x here is to the right of this, which means x has to be greater than 2 minus delta. Now if we take this value here and we subtract 1, it reads 2x greater than 4 minus epsilon. Divide by 2 and we get x greater than 2 minus epsilon over 2. Oh boy, and you know, oh no, yeah, no, we're good. Okay, now what we're going to do is we're going to compare this right here. And we're going to say 2 minus delta greater than 2 minus epsilon over 2. Subtracting 2, we get minus delta greater than minus epsilon over 2. Dividing the minus sign out, we get delta less than epsilon over 2. Okay, so what we have here is a delta on one side of that equation here. I'm going to take this now and store this. Any delta less than epsilon over 2 will mathematically absolutely guarantee that our function will be closer to the limit, meaning up here, not down here, than the 5 minus epsilon. Now we're not quite done yet. Now we're going to take a look at the other side. All right, so imagine a point over here. Right there. Now, first of all, we need x to be to the left. Mathematically, that means less than 2 plus delta. Now, we look up here now. Notice that the function, we need to be less or below 5 minus epsilon. So our function here now is 2x plus 1. We need to be less than 5 plus epsilon. Now, this thing right here, let's see, if we subtract the 1, we're going to have 2x less than 4 plus epsilon. If we divide by 2, it's going to read x less than 2 plus epsilon over 2. Kind of comparing these two right here. If we take 2 plus delta less than 2 plus epsilon over 2, and we subtract 2, this is now going to read delta less than epsilon over 2. So what we have is a pair of deltas now. One from one side of the function, one from the other side of the function. They ended up being the same because it's a linear function. That's the only example I'm aware of that'll happen. Right? If this was any other function, quadratic, cubic, sine function, you name it, we would have two different deltas, a delta 1 and a delta 2, I'll call them. And suffice to say, one is smaller than the other. So you typically choose the smaller of the two deltas. So right now, I'm going to say this. Any delta less than epsilon over 2 guarantees that the function is inside of this distance, mathematically guaranteeing the limit is equal to 5. So the idea behind a limit proof is you tell me an epsilon, can you find a delta that guarantees the function is in this value between L plus epsilon and L minus epsilon? That mathematically proves the limit is a certain value here, and I have one right here. Since I have delta equals epsilon, delta, any delta less than epsilon over 2 mathematically guarantees this. So can I find one? Sure. Delta epsilon over 3, epsilon over 4, epsilon over 5, all of those are less than epsilon over 2. So that's the idea behind a limit proof. These tend to throw people for a little bit of a loop. They're not, I don't believe, super critical to being successful in understanding calculus. I think it's okay for now. Can you get some of these done and come up with a deeper understanding as you get more experience in the course or with the topic? But anyway, there's an example of an epsilon delta proof. I've got more videos for you to look at it as needed. Yeah, have a great day.